So, hi everyone. In today's session, we'll understand Wiener process. So, yesterday, in last session, we saw how binomial tree can be used to price options, right? European option or American option. But in this session, let's see, so let's see what is Wiener process. And this is, the foundations of stochastic calculus. So specifically in stochastic calculus all these concepts becomes very important. So and these are the stepping stone for any model that you see, be it Brownian motion, sorry, be it Black-Scholes models, my bad, be it Black-Scholes model, or be it any interest rate model such as Vesi-Check model, CIR model. There are so many, interest rate models, even like the volatility based, stochastic volatility based models, right? So, such as Saber model, CEV model. So these, Wiener process becomes, or you can say that Wiener process is the foundations of all these models. So that's why it's very important for all of us to understand first what is Wiener process. So, okay, so coming back to the formal definition, just let me remove this. Okay, so coming back to the formal definition of Wiener process. So first let's understand what is it. Okay, so let me write the definition first so that it's easy for all of you to comprehend. Okay, so okay, so even going, okay. So do you all know, or does anyone know what does it mean by a stochastic process? Do you all know what does it mean by stochastic process? So the word stochastic, when it comes to quant finance, right, the word stochastic means random process. Okay. So the word stochastic means random. Okay. So the word stochastic mean random. Okay. So we are trying to, so if you see, in the world of finance, we say that stocks are random processes. Okay. And that's why. And why do we say that? Even let's think, why do we say that? Because let's say if you see in a given day, let's say if you see in a given day, when the trading starts, you will see the stock price going like this, like this, like this, like this, like this. There's no fixed pattern, right? It can go like this, it can go like this. So in the world of quant finance, we say that this whole process is stochastic in nature, or we can say that this whole process is random in nature, and we are trying to model the randomness. Okay, so we are trying to model the randomness. Okay, this is just for all of you to understand what it means by the word stochastic process. Okay, so now coming back to what is a Wiener process. Okay, so any variable whose value changes over time in a certain way. Okay, so let me uh, okay, first, let me write this for you. So, what is stochastic process? And then let's come to Wiener process. Okay, so the formal definition of stochastic process is any variable whose value changes over time in a uncertain way is said to be a stochastic process. Okay, so if you see this, let's say if you see any stock, following this pattern, so they say that the stock, we say that the stock follows stochastic process. Why do we say that? Since it's random in nature. Okay. So now stochastic process, this whole process that you see can be divided into further two types. That is a discrete, a discrete time and a continuous time. So, so what are two types of stochastic process? One is the discrete time stochastic process, and the other one is continuous time. So what is discrete time and what is continuous time? Let us look at it. So let's see discrete time. So a discrete time stochastic process is a process in which the value of the variable can change only at certain fixed point in time. Okay. So a discrete process or a discrete time stochastic process is a process in which the value of the variable can change over a over certain fixed interval of, or you can say over certain fixed point in time. Okay, so this is what it means by discrete time stochastic process. So, and the second is continuous time stochastic process. Okay, so what is continuous time stochastic process? So, a continuous time stochastic process is a process wherein the value of the variable can take place at any point in time. So, a continuous time stochastic process is a process wherein the value of the variable can change at any point in time. So just remember for a discrete, so stochastic process means it's a random process. So a discrete time stochastic process is a process in which the value of the variable can change over certain fixed point in time. Okay, this is important. Whereas for a continuous time, it's a process in which the value of the variable can change at any point in time. Okay, so this is very important for all of you to understand. So don't worry, we'll see a lot of examples. I know you are looking out for examples, but we'll see a lot of examples in the coming, in the rest of the whole session. So, so before understanding, or before diving deep into the world of stochastic process, one very important property is Markov's property, and this is very important. So let's understand Markov's property. Let's understand Markov property. Just give me 1 second. So Okay. So you have asked examples, right? Guys, I understand you have a lot of doubts, but let me complete first so that it makes it will be easy for all of you to follow. So okay, so let's understand. So we'll okay, just for example, we'll cover a lot of examples in detail with the Excel implementation. Let me reach at that point. But just for you, for all of you, example for continuous processes, geometric Brownian motion. We'll see all of this in today's lecture, so don't worry. And I also have an Excel implementation for all of them, so it's easy for all of you to comprehend. But don't worry, we'll cover everything in detail, okay? Don't worry. Even with the examples also, there are a lot of examples in there, so we'll cover everything. Okay, so first of all, what is a Markov property or what is a Markov process? Okay, so let's understand what is Markov process. See, Markov process is a particular type of stochastic process wherein the current value of the variable is relevant for predicting the future. Okay, so what is Markov process? So Markov process is a process, or so it's a type of stochastic process. Okay, it's a type of stochastic process where the current value of the variable is relevant for predicting the future. See, the end goal of any stochastic modeling that we are trying to do in the world of quant finance is to predict what's gonna happen in the future, right? So whatever we will study in terms of modeling, we'll try to see what's gonna happen in the future. So what is Markov process? It's a process wherein the current value of the variable is relevant for predicting the future value, but the past values of the variable are irrelevant. So what is this property trying to say? Or what is this process trying to say is basically, let's say you have a variable, right? Let's say this is the value at t0, this is the value at t-1, t-2, and so on, right? And this is t+1. So what this process is trying to say is to predict what's gonna happen here. To predict what's gonna happen here, we just need the present value. That's it. All these past values are irrelevant. Okay, so all these past values are irrelevant to us. What is relevant? The current value. That's it. The current value is relevant to for what? To predict the future. Okay, so let's define the property. So the property Markov property states that the future state of a process depends only on the present state. Okay, so the future so what does this process says that the future state of a process depends only on the past state, not on its past values. Okay, so how can we write this in terms of in mathematical terms? So for a stochastic process, x xt, okay, where t is greater than 0. So this stochastic, so this will satisfy the Markov, it satisfies the Markov's property when, satisfy the Markov property when the probability of x t plus 1, given that x t minus 1 up till x naught is equal to probability of x t plus 1 given that x of t. Okay. So what does this thing says? Okay, let me tell you. See, so this is very easy to understand. So what we are trying to say is x t plus 1 is the thing that we are trying to predict. So this is t plus 1, this is t minus 1, and so on. Okay, and let's say this is t naught or whatever it is, right? T minus 1, t minus 2, and so on. Okay. So what we are trying to say is to predict what's gonna happen here. To predict what's gonna happen here, given that we have all of this, it's same as probability that we are trying to predict this given this value. So essentially, why this property or why or what this property is trying to say is we do not need the historical data. No need of historical data. No need of historical data. Okay, we just want the current value. We just want the current value. Oh, my bad. Yeah, we just want the current value to predict what's gonna happen in the future. Okay, so now you might be thinking, but Mehul, like if you see stocks, right? So we are, because the end goal of any stochastic, so one of the application of stochastic modeling is in the world of finance, is in the world of stocks, right? That we use these stochastic processes for modeling of a modeling stocks. So you might be thinking, but like how it is valid for stocks, right? Because you might be thinking that, oh, we need 10 years of data, 5 years of data to model stock prices. But what this process is trying to say. So let's say the value of a stock XYZ is $100 today, and let's say this 5 years back, 5 years ago, the stock price was $20 and now it's $100 in this 5 years. Okay. So what this process is trying to say you is whatever price we have today, it captures everything what has happened in the past. Okay. So whatever price you see today captures everything that has happened in the past. Do you all agree or not? Do you all agree with this statement or not? Okay, perfect. So basically, so that's why we say this, that this Markov process is memoryless. So that's why we say that Markov process is memoryless. That is, the current state contains all the information n- needed to predict the future. Okay. So this term is very important. This is also been asked in interviews that or why the macro process is memoryless. So you need to say that because whatever value we have of the variable in the current state, we can utilize that for predicting what's gonna happen in the future. So stock prices in general, they are usually assumed to be a Markov process. Okay, so note. And see, one more thing that you have to now understand is we are moving into the world of quantitative modeling or quant modeling, right? So these are stuff that that you should understand, like what's the reason behind that, okay? So you will see a lot of mathematical piece, statistical piece that we will that is very important in the world of quant modeling. So we'll definitely do the mathematical and statistical piece, but this is just the theoretical part. So note that stock prices are assumed to be Markov process in the world of quant modeling or in the world of quant finance. Okay, is it clear to everyone? Okay, so let's see what is the relevance of Markov property in the world of quant finance. And with for the examples of the discrete time continuous process, continuous time discrete time stochastic process and continuous time stochastic process, I'll tell you all the examples, but I'll have to show you, because if I just write names, you won't understand. So that's why I want to first show you, and then in the end, I'll conclude that okay, for stochastic processes, these are the examples. Sorry, for discrete time stochastic processes, these are the example. For continuous time, these are the example. So I'll show you certain practical implementation also. So you'll really love it. Okay. So let's see what is the relevance of of Markov property in quant finance. Okay, so let's see. So this is the first application in the world of quant finance's option pricing. Okay, so it is very helpful for option pricing. So if you see that there is one model which is called the Black-Scholes model. Okay, there's this model which is called the Black-Scholes model, which is used to price European option. Okay, this is used to price European option. So the Black-Scholes model assumes that the underlying asset follows a geometric Brownian motion, which is nothing but a Markov process. Okay, so the Black-Scholes model, the Black-Scholes model assumes that the stock price follows geometric Brownian motion. Okay, so the Black-Scholes model assumes that the stock price follow a geometric motion, Brownian motion, which is a Markov process. So we'll see how to simulate stocks using GBM. Don't worry, we'll see all of them. But this is just for all of you to know that this is uh, where Markov property is used. First of all, it's used in Black-Scholes model. Now the Black-Scholes model is been actually being used to price European option. So this is the first. Second application is modeling interest rates. Okay. So what does it mean by modeling interest rates? So, there are a lot of stochastic interest rate models, okay? There are a lot of stochastic interest rate models. What are they? Such as Check, CIR, Hull White model, Holy model. There are a lot of models like this. So if you see all these models, uh, they they consume Brownian motion. Okay, so all these models, one of the most integral part of that is Brownian motion. And Brownian motion property is what? Markov. So Brownian motion follows Markov property. I totally understand. You might not be knowing what is Brownian motion. Don't worry, we'll cover that. I'm just telling you where is this used. So a question asked by Gino is, where is GBM used in Black-Scholes model? See, understand one thing. What you're looking, so I'll cover that in detail, but just to answer you, what you're looking at is in the question you mentioned ND1, ND2, right? What you're looking at is just the final formula. But how was the formula derived? The first thing that the formula assumed was that the stock follows GBM, and then they did the derivation, and that's how the BSM Black-Scholes model formula was built out. Okay, so if you see the derivation, that's where you will understand, and that's where you will understand why GBM or how GBM was used. But this will cover in detail, guys. Don't worry, this will cover in details. So this is all about Markov property. So just to summarize, what is Markov property? Markov property says that if we are trying to predict something in the future, we can predict that thing just by using the current state. Okay, so whatever value we have at t, we can use that to predict at t plus 1, and the past values are not relevant. Okay, so now moving on to what is Wiener process. Here I mentioned about so Brownian motion. So let's see what is Brownian motion, or what we also say that as Wiener process. So what is Wiener process, or you can also say as Brownian motion. Okay, so let's see what is this. Or you can also say, so these Brownian motion and Wiener process are just synonyms. Okay, so let's understand what is Wiener process. So Wiener process is a continuous time stochastic process. Okay, so Wiener process is a continuous time, and you all were asking, right, certain examples. So this is the example of a continuous time stochastic process. Okay, so Wiener process is a continuous time stochastic process that models random motion. Okay, so the Wiener process is it is widely used in physics and finance. Okay, actually the whole concept of Wiener process, it came from physics and then it was utilized in finance. So this is actually a mathematical process which was utilized in physics. Okay, so this whole process was derived in physics, but because it's such an interesting process, we actually use it in finance. Okay, tell me one thing. Let me show you how a Wiener process look like. Tell me one thing. If I capture a insect or a fly, let's say this is a fly, okay? Mosquito or honeybee. You can say anything, okay? So let's say this is how it looks like, and we have captured this in a container, in a closed container, okay? So we have captured the honeybee in a closed container. Tell me one thing. What will be the direction or what will be the movement of this honeybee? It will be random. It can go anything like this. Agreed or not? Can you say that, oh, this is the only way that the honeybee will travel? Can you say that? No, right? You cannot say that because we do not know like how the honeybee will travel. It can travel in any direction. It can, this honeybee can go left, then straight, then right, anywhere. And that is what our Wiener process is. That is what Wiener process is, or what we say is Brownian motion. So what is this process? This is nothing but random in nature. It's a random process. Okay, it's a random process. So what we are trying to do using the Wiener process, we are just trying to model the continuous random motion. Okay, we are trying what we are how we are trying to use this Wiener process or this Brownian motion. Why is it called the Brownian motion? Because it's there's it can go in any direction. There's no fixed direction that the honeybee will travel. So in our case, in the world of stocks, right? If you see in the world of stocks, right, or in the world of so in the world of stocks, you see this stock price can go like this in any direction, right? It can go in any direction, and that's why we say that the stock follows Brownian motion, more specifically geometric Brownian motion. But we'll come to that. But let's understand Brownian motion, because once we understand Brownian motion, the next step is to understanding geometric Brownian motion. Okay, but just to clarify, what is Brownian motion? It is of Brownian motion, or what is Wiener process? It is a continuous time stochastic process that models the random motion. Okay, so let's define it in mathematical terms. Okay, let's define it in mathematical terms. So mathematically, a Wiener process is denoted by W t, where t is greater than equal to 0. Okay, so mathematically it is defined like this. And And as I said, so mathematically, a Wiener process is nothing but what is this? It's a continuous time stochastic process. Okay. So let's see certain properties of the Wiener process. Okay. Let's see certain properties. So it is always remember it is denoted by this. Okay. WT. So let's see what are the properties of Wiener process. See, when someone says Brownian motion or Wiener process, it's just the same. They are not different. It's same as it's like the synonyms. Okay, it's just the synonym, don't worry. Okay, so what are the properties? Okay, the first property is, and see, properties are very important because these are some interview questions that can be also asked in your interviews. Okay, that what are the properties of Brownian motion? So to qualify as a Wiener process, it must satisfy five properties. Okay, it must satisfy five properties. First is initial value. What is the first property? It says that the process should start at zero. Okay, so this is the first property, that the process, the Brownian motion, or you can say the Wiener process, should start from zero. So what does that mean? That basically means that the first value of the Wiener process is zero. So so W naught is zero. So this is the first property. Okay. Second, second property is independent increment. What does this property say? It says that the change in the process, let's say the change in the process are independent of each other. Do you all agree or not? Do you all agree with this statement or not? This is what it means by Markov's property, right? If you all remember, let's say this is t, sorry, let's say this is t plus s, okay, where s is some interval, okay. So what this property is saying, that w of w of t plus s minus w of t, okay, this is basically independent of each other. And we also agree to this statement. Why? Because we all know that, let's say, if we have captured the honeybee, if we have captured the honeybee in a container, let's say this difference s is nothing but 1 second, okay. Let's say this value of s is 1 second. So in 1 second, this can basically go here, here, here. We don't know where it will go, right? Because we don't know how the movement of honeybee will be, right? So that's why they say that basically the change in the value, or the change in the process, what, so whatever value you see here, okay. So whatever value you see here versus whatever value you see here, those are totally independent of each other, and this is nothing but Markov's property. Is it clear to everyone? Is it clear to everyone? Okay. So the third property is normally distributed increments. So what does this normally distributed increment mean? So what it says is, for any s greater than 0, s is the time interval, always remember. The change, what is the change? We all know change is nothing but wt plus s minus of wt. This is normally distributed. Okay, and this is very important property. I really want to make you all understand, this is very, very important. So what we are essentially saying is, the change in the process is normally distributed. Okay, so the mean, so basically when I say this n of 0 comma s, what does this mean? That the mean is 0 and the variance is what? S, which is nothing but proportional to the time increment. Okay, is this clear to everyone? Is this clear to everyone? Okay. So always remember that this process, the change in the process. So let's say you have wt here, you have wt plus s. So when you, so you, let's say you have some value here and some value here. Okay. So when you difference this value, both the values, when you take a difference of both the values, that will follow a normal distribution. Do you want me to show this in Excel? No. So variance, that's a very good question. Is the variance of the process not equal to 1? So because it's a Brownian motion, the variance is always equal to the, is, or variance is always proportional to the time increment. So the time is increasing by s. If you see in our process, if you see what is the time, what is the increase in time, t plus s minus t, which is s. So this is nothing but change in time, right? Change in time is what, t plus s minus t, which is nothing s. So what, so this property, what this property says that the time, it's the variance is equal or is proportion to the time increment. This is the third property. Okay. Do you want me to show this property in Excel? Can you all? Okay. Okay. Excel implement. Okay. So just let me cover this, and then I'll show you how can we how in Excel it looks like. Fourth is continuous path. So what does this process say? What does this property say? That the Brownian motion or the Wiener process should evolve smoothly over time. So which basically means that there should not be any jumps. Okay. The Wiener process should evolve smoothly over time. Should evolve smoothly over time, which basically means that there should be no jumps. So let's say, have you ever seen any stock price going like this, and then you will see a gap and then it starts again? No, right? You will never see something like this, right? In the world of stocks, it will be always continuous. It will be always continuous. There will be no gap. There won't be, any gap. It is always continuous, and that's why this property is very important, that it should not have any gaps or any jumps in between. It should be always continuous in nature. Because always remember, Brownian motion or Wiener process is a continuous time stochastic process. It's not a discrete time. If it was a discrete time, then it was allowed, this thing was allowed. If it was a discrete time stochastic process, then we would have said, okay, this is allowed. But since it's a continuous time stochastic process, that's why we say that there are no jumps allowed. There are no, and when I say jumps, I do not mean like jumps like this or like this. I do not mean this. Jumps basically means this wide space. Okay, there's no this space allowed. Okay, it is not a discrete time, it's a continuous time stochastic process. So CTSP is nothing but continuous time stochastic process. Okay, continuous time stochastic process. And the last property is variance is proportional to time. It's actually covered only, so but I'll just write variance is proportional to time. What does this mean? That the variance of the Wiener process, variance of the Wiener process grows linearly with time. So this is again captured in the so we can remove this actually, because it's already been captured. So let me remove this. Because why is that? Because it is already been captured in the normal distribution thing, right? If you remember this, we say that, if you remember this, we say that this S is what? That are it's a basically, if you remember that the variance, if you see S is what? The variance, right? Variance grows linearly with time. Okay, so variance grows proportional to the time increment. So we have already captured that, so there's no need of it. So let me show you an Excel implementation of how the whole things look like. Okay. So let me share my screen. Just give me 1 second. Uh, can you all see my screen? Let me know if you all can see my screen. Okay, perfect. Let me, just give me 1 second, guys. Okay, so let us first understand how we can perform this. How can we generate the Brownian motion in Excel? And this is very important for all of you to understand. Okay, so first of all, see, Brownian motion is what you all have understood. It's nothing but a random motion, right? It's a random motion. It can be anything, right? So the first thing that we are trying to do is we are generating a random variable. So the first thing what we are trying to, so if you see column B, okay, column B, it is nothing but we are trying to generate a random variable. Okay. Okay. So column B is nothing but column B. If you see, we are trying to generate random variable. So how can we generate the random variable? So it can be generated using norm.s.inverse. If you see this formula, rand, so rand and then brackets. So basically, this will generate a random number. So this is how you generate a random number in Excel. Okay. Is it under did you all understand how did we generate? So once you generate this random number, so okay. So let me write this norm dot sorry norm dot s dot inverse. Okay, and then you need to write the probability. So we are saying that the probability is random. We don't know what is the probability, it's just random. Okay, and okay, so I just did a small, yeah. So this is how it will generate probability, and like this will generate thousand random numbers. Okay, if you see in total, I've generated thousand random numbers. Then the next step is delta t. So we all know that in 1 year there are 252 trading days, right? In 1 year there are 252 trading days. So what will say is, okay, we are just using square root of 1 by 252. This is more of generating the delta. Okay. Okay. So understand. Okay. Let me write the formula for all of you for Brownian motion. Just give me 1 second. So that is easy for you to understand. Okay. So this is the formula where sigma is 1, z is nothing but our random variable, and t is nothing but our time. Okay. So let me check one more thing. Yeah. Okay. So the first thing is, see, if you just see this formula, if you just see this formula, when sigma is 1, when sigma is 1, the whole formula becomes Wt is equal to Wt minus 1 plus square root of t times z, right? This is what the formula becomes, correct or not? Do you all agree? Do you all agree with the statement when sigma is 1? Okay, so a question asked by Gino is why t minus 1? So if you all remember what was Brownian motion, it follows Markov's property, right? It follows okay, so either you write, okay, so you can also write this, okay, Wt plus 1, Wt plus 1 is equal to Wt plus sigma times square root of t times z. It's the same thing. Okay, it's the same thing. If I just write t, then I'll have to use t minus 1. If I am writing t plus 1, I'm predicting, so I'm predicting t plus 1 using t. So let's look at this. Okay, let's take this. Okay, so okay, so a quick question, question, okay, okay, so a quick question asked by Parivesh is why cannot we use a random function? So there's in Excel, if you see, there's this random function also, right? If you see this random function, which can be equally used to generate random numbers. But the reason, but the why we are using this formula norm dot s dot inverse rand, why we are using it? Because so that we can get standard normal distribution. Okay, we can get standard normal distribution. So if you see here, this is standard normal distribution is what we are trying to generate. If you all remember, what we were trying to take this assumption, right, that the random number should be normal distribution, right? As we all saw in the theoretical piece, that the increments are normally distributed, something like that. There was this thing, right? So first thing we have to do is we have to generate our random numbers, right? Now see, because we have to consider square root of t in our calculation. We know that in 1 year there are 252 trading days, right? So if you see, how will you write 1 day? So you will write 1 by 252 as 1 day, but we all know that we have to take square root. So I have just taken this square root of, okay, square root of this 1 by 252, which is, okay, so square root of 1 by 252, which is nothing but 0.06299, and that's what you see here, right? And why is it constant? Why is it constant? It is constant because we are considering 1 day only, and that's what will flow throughout. Okay, so now, what is the Wiener process formula? If you see, Wiener process is nothing but Wt plus 1 is nothing but Wt plus sigma times square root t times z. See, sigma. So what I've done is I've taken sigma as 1. Okay, I've taken sigma as 1. Okay, because it's a standard, so it's a standard normal distribution, right? So that's why I've just considered sigma as 1. So what we see is, okay, before that, a very important thing. We all know that the Wiener process starts with 0. This was the first property, correct? Do you all agree or not? The Wiener process that we saw recently started with 0. So when we are trying to predict the next value, which is this value, what we'll do is we'll take the previous value, which is W naught, which is 0. If you see, this H1 is nothing but our previous value, which is 0. This plus C2, which is nothing but our delta t, square root of t times our random variable, which is z. Okay, and sigma we have considered as 1. Okay, so this is how you will model the first increment. Now, because we all know that it starts from 0, it is totally fine to model the Wiener process for the first step. But now when you are modeling the second step, when you are modeling the second step, what will you do? If you see, oh, okay. Okay, when you are modeling the second step, what will you do? You'll consider the previous step, right? Which was WT. Okay, and then you'll use the same formula, which is nothing but sigma times square root of t times z. Sigma is 1, so I have not specifically included, but yeah. But this is how the formula will look like, and throughout we are generating, let's say we are generating 1000 steps. Okay. So now, to prove whether the no, whether the increment follows a normal distribution, tell me one thing: how can we calculate the increment? Increment can be calculated like this this subtracted by this, correct or not? What, so if you see what is the increment? Increment is nothing but this is what the process has been followed, right? So what is the increment in the whole process? Nothing but subtraction of these two. Similarly, subtraction of these two, this is the increment, right? Agreed or not? Do you all agree with this statement? Okay, perfect. So now we are trying, let's take a histogram of this. Okay, when we take a histogram of this, so if you see, this is when I capture the histogram, this is how it looks like. So if you all visually see and tell whether this is a which distribution it is. It is nothing but a normal distribution. See, it is nothing but a normal distribution. Okay. Whatever times I'll generate the process, whatever times I'll generate the process, it will always be a normal distribution. And why is that the case? Because that is what the property says, right? The increment will follow a normal distribution. And this is how the normal distribution will look like. Okay, just an example of how the distribution look like, but this is how a normal distribution looks like in general. So is it all clear to everyone? How does the increment follows a normal distribution? Is it clear? So it's a simple process. What we need to do first, make sure that first we generate random numbers. Then the first process is nothing, we know it starts from 0. Then to calculate the next step, it is nothing but 0 plus, we'll multiply the random number with this, okay, random number with square root of t. Also remember one thing, also guys, remember one thing, that for a standard normal distribution, for a standard normal distribution, mean is always 0 and variance is always 1. So if variance is 1, what is sigma? Sigma is nothing but square root of variance, right? Sigma is nothing but square root of variance, and that's why you'll see sigma is 1. Okay. This is the property of what? Standard normal distribution. Okay. This is the property of standard normal distribution, that the mean is 0 and the variance is 1. Okay. And then if you see, if you see what we are trying to do, so if you see what is the Wiener process, as I said, the formula is nothing but wt plus 1 is equal to wt plus sigma, which is 1 in this case. So 1 times square root of t times z. Okay. So is it, and then we'll basically plot, will calculate the Wiener process for each step. Just remember, for the first step, it will take 0, and from the next step it will take this, okay, this value. Okay, the previous value. And that's how we'll build this whole Wiener process. Okay. Do you want to see how does this Wiener process look like? So let's see how this. Okay, so let me show you how this Wiener process look like. If you see, this is how the Wiener process look like. Okay, which basically means that it is totally random in nature. See, I'm just generating new values of it, and it is even if I generate 100 times, you will never see anything being followed. Okay, you will always see that it is every time it is giving a new shape, and that's why it helps us in the stock modeling. Why? Because even in stocks, when we have to simulate thousands of path, okay, like this will be simulating thousands of path, and then we'll be using those in our derivative pricing. Okay. Okay, is it clear to everyone how Wiener process is being generated, and then why how the increments? So this is nothing but increments of Brownian motion. This is not Brownian increments. Okay, increments of Brownian motion, which follows a normal distribution. Clear to everyone? Is it clear? Can you give me a heads up? So we'll cover, I guess, a question asked by Gino is, would there be a mean reversion here? We'll cover mean reversion, don't worry. We'll cover mean reversion. Yeah. So, Sheikh asked, why do we assume normal distribution in real life? That is not always true. I totally agree that normal distribution in real life, it is not always true, because if you see the pandemic 2020, which, the COVID hit, and we saw that, equities, stocks were not following the normal distribution. But the beauty of normal distribution is that it has a lot of statistical piece. It has mean, it has variances, it has skewness, it has kurtosis. Okay, there's a lot of statistical piece, and when you have different statistical piece, it really helps in the modeling world. Okay, so it is very, so when you have why we always consider normal distribution, the only reason is because it has a lot of statistical piece, or it has a lot of statistical significance. And that's why using normal distribution is very very easy. And I'm not denying that only use normal distribution. There are a lot of other distributions like student t distribution, variance gamma distribution, that are also used in the for modeling stocks. But let's cover the basics, because this is just the starting point. So let's cover like the starting point. So is it clear to everyone how this was derived? Why do we say that it's normally distributed, the increments are normally distributed? Okay, perfect. So let me get back to my screen, and let me write other stuff which are important to this. So this is what we covered recently using the Excel implementation, that the for any increment, the increments are normally distributed. Okay, this is what we recently covered using our Excel implementation. And this is what you also saw, that there was a continuous path, right? There was no jumps, or there was no abrupt, discontinuity in the process. It was always continuous, right? So this also so what did we confirmed? We confirmed this thing. We confirmed this thing, right? We confirmed Markov property. How? If you see how, because we were trying to model, if you see what we were trying to do, we were trying to model, let's say this was the line, we were trying to model this thing using this, right? We were not using this, only the previous increment only, or the previous step only we were using. So we also verified this, which is independent, and we also saw this, that we consider W naught as 0. So this whole thing was been verified using an Excel implementation, which is the properties of Wiener process. Is it clear to everyone? Okay, perfect. So let's look at certain other things also at the same time. Okay, also one more thing is one property that I missed. Wiener process is also martingale. Sorry, one property that I missed. Wiener process is also martingale. Do you all know what does it mean by martingale? Do you all know what does any anything which you all know? Yeah. I'll just wait for a few seconds. Okay. Okay. So let's see so Wiener process is martingale. Let's see the easier way to understand. So let's see what is martingale. So martingale process, what is it? So it is nothing but a martingale process. A martingale is a process A martingale is a process where the future expected value is always equal to the current value. Okay, so what does this mean? This, so let's say for a Wiener process, okay, let's understand this. For a Wiener process, which is WT, Wiener process WT, right? At any point t, at okay, at any point, at any time t, the future value WT plus S for any S greater than 0 depends only at depends only on where is it is depends only on where it is at time where it is at t, not not on how it's gone there. So mathematically, how can we define this is so mathematically how we can define it is something like this. Expectations of W of t plus S given WT is equal to WT, which basically means that what does this mean? This basically means that the best guess for the future value is just the current value. Okay. Okay. Do you all understand what does this mean? Basically, if you see what is a martingale, it's a process where the future expected value is always equal to the current state. So for a Wiener process, at any time t, the future value WT plus S depends only on where it is at time t and not how it's gone there. Okay. So let's see certain statistical piece which is equally important on the derivation part. Okay, so okay, so let's see. So let's see the statistical piece. Okay. So if you all know, I mentioned that the expectations, or if you see, did I mention that? Okay. Okay, so let's try to prove this point. Let's try to prove this point. Okay. So why is this okay? Okay, so let's see. So let's see. And this is, also asked sometimes that the expectations of a Wiener process is zero. Expectation of Wiener process is zero. Expectation is nothing but it is nothing but it represents the average value. Okay. So expectation, whenever I say expectation, it basically means the average value. Okay. Average value. Or you can also say that as mean. So we need to prove that the expectation of the Wiener process is zero. Okay, let's see how can we prove that. So so we need to prove that expectation of Wiener process is zero. Okay, tell me one thing, or we can write, let's say, let's write this xt. Let's define our process wx, which follows a Wiener process. So this is what we need to define. Okay, so tell me one thing, from the Brownian motion definition, or from the Wiener process definition, can I say that xt is equal to x naught plus sum of independent increments? Can I say this? Can I say this? Xt is nothing but x naught plus sum of independent increments. Can I say this? So if you see, so let's take expectations of everything. Expectation of xt is expectation of x naught plus expectation of, what is sum of independent increment? Can I write this as delta x? Right? Sum of independent increment we can write as delta x, right? So we know that, first of all, we know that x naught is 0. So therefore, expectation of x naught will be also 0, right? When x naught is 0, the average of this value will also be 0. Correct or not? Correct or not? Okay, now if you see delta x, we know that it follows normal distribution. It follows normal distribution with mean of 0. Okay, so if you see, expectation of xt is nothing but expectation of x0 plus expectation of delta x. Okay, what is expectation of x0? It's 0. Expectation of delta x, we just saw that delta x is normally distributed, okay, with a mean of 0. So when we say mean of 0, it is also 0. So that's why e of xt is nothing but 0. Do you all agree? Do you all understand how did we come up to this? So similarly, do you all understand how did we come up to this? Okay. Similarly, if you see, let's see variance. Let's calculate variance, right? We know that variance of xt is what? We were told that variance of this process is equal to the time, right? Okay, so Mahesh has to go through it quickly again. Okay. So see, this is what we are trying to prove, that the expectation of the Brownian motion or expectation of Wiener process is 0. Okay, basically what we are saying is that the mean or the average of whatever value the Wiener process takes, it is 0. Okay, this is what we are trying to prove mathematically. So if you see, what is xt? What is this whole Wiener process? It is nothing but the starting x naught plus some of the independent increments, right? So we can write mathematically in this way that expectation of xt is nothing but expectation of x naught plus expectation of delta x. Delta x nothing but delta x is what? Sum of independent increments. We know that, we just saw that Wiener process always starts from 0. So we know that for a fact that x naught is 0. So that's why when the process is 0, average of it will be always 0, also 0, right? Similarly, if you see delta x, if you see delta x is what? Normal distributed, right? We just proved in Excel that the increments are normally distributed with a mean of 0. So when delta x has a mean of 0, when delta x has a mean of 0, what does that mean? That, if you see, this was what we wrote, expectation of xt is nothing but expectation of x naught plus expectation of delta x. We know that this process starts from 0, so the mean is 0. And this process, it is normally distributed with a mean of 0, so both are 0. So that's why overall process, the expectation of the whole Brownian motion is nothing but 0. Okay, perfect. Now let's prove. the variance of xt is t. This is, let's prove this, okay? This is what is given to us. Sorry, this is what we have to prove. See, can I write this thing something like this? Variance of xt is equal to variance of delta x1 plus variance of delta x2 and so on. Can I write this? Can I write this? Okay. So what is variance of delta x? What is variance of delta x? It is nothing but delta t. So variance of, let's say, if there is a process, it went from here to here. What is the variance? It is nothing but variance will be the time interval, which is delta t. Okay. So now can I write this statement as, can we write this statement as n variance of xt is equal to n times delta t? Because we know that for this is delta t, this is delta t, this is delta t, and so on, right? So this becomes n time delta t. Now tell me one thing. These all are delta t, right? Delta t, delta t, delta t, delta t, and so on. When I do n times delta t, it gives me nothing but t. So this is nothing but t. Okay. So that's why we say that variance of xt is nothing but t. See this, I'm just showing it. There are other way also. There's one more way which, for proving the variance of xt, which is more like this. Uh, so there's one more method of proving this whole derivation. But I thought like let me simplify it for all of you. So this is how you can all understand, right? So how is variance of xt is equal to t? How is that? Because variance xt can be written as the small process, right? Okay, so a question asks this: can we not add x naught? Yeah, we can add x naught. But if you remember, when mean of x naught is what, 0, so variance will also be 0. Mean and variance both are 0 for this process. Okay, so that's why you write or you don't write. It's the same thing. Okay, you write or you don't write, it's the same thing. So 0 plus delta t plus delta t plus delta t. So this whole equation will look like this, delta t up to, you know so this is nothing but n times delta t, right? And which is nothing but t. So that's why we say that the variance of the whole process is nothing but t. Okay, perfect. Okay, so that's why if you see, coming back to our property, we say that, okay, coming back to our property, we say that our Wiener process or our Brownian motion is normally distributed with a mean of 0. We just proved how it's 0. And S is nothing but time. Okay, S is nothing but time. Okay, did you all understand? How did we arrive at this property? So first we proved that, okay, the increments are normally distributed. And then now we just proved that how it is 0, how the mean is 0, and how the variance is equal to the time. Okay, in this case, what is the time? T plus S minus t, which is nothing equal to s. Okay, so is it clear to everyone? Is it clear to everyone? Okay, perfect. So guys, this was all for today's class, because I want to cover geometric Brownian motion. So we saw like the Brownian motion, we saw Brownian motion. So I want to cover geometric Brownian motion and Black-Scholes modeling together, because that will be easier for you to understand, because these are correlated these are very much related. So this was all for today's lecture. But in next class, we'll see geometric Brownian motion and we'll see Black-Scholes modeling. So let me stop recording.